is not undergoing any chemical reaction or phase change. Entropy gives the measure of randomness. Now, what is the physical significance of entropy? It gives. So, three different conditions are given and we have to find out the value of delta S for each case. Hello students, welcome to Alan Overseas and welcome back to the very important series that is 45 important topics in 45 days. So as you know that this series is divided into three parts, that is 15 topics of physics, 15 of chemistry and 15 of mathematics, and I will be discussing this chemistry part with you, right? So let's start with the next topic of chemistry, and that is enthalpy, entropy and Kirchhoff's equation taken from the chapter Thermodynamics, right? So now, first of all, let's start with this topic, and first of all, we have enthalpy. So basically here, you know that thermodynamics is not a small chapter. We have taken these three important topics, and here regarding enthalpy, we are going to talk about the relation between enthalpy and internal energy, the change in enthalpy and change in internal energy, right? So as we know that enthalpy is the energy change taking place at constant pressure, right? And the relation between delta H and delta U. So basically the difference between these two, delta H and delta U, becomes significant only when gases are involved in the process, in the reaction, okay? It is insignificant in case of solids and liquids, okay? Because the change in solids and liquids at constant pressure or constant volume is negligible. That's why the difference between these two properties for solids and liquids also becomes insignificant, right? So basically this relation is useful when you have gases involved in the process or chemical reaction, right? So this is the relation between these two, delta H equal to delta U plus delta PV, okay, where delta H is enthalpy change, delta U is internal energy change, and P and V are pressure and volume, right? Okay, so when substance is not undergoing any chemical reaction or phase change, then we can use this relation, that is delta H equal to delta U plus NR delta T, where N are the number of moles, R is the gas constant, and delta T is the change in temperature. And when we are talking about a chemical reaction, then this relation will be useful, delta H equal to delta U plus delta NGRT. Now, what is delta Ng here? If we talk about delta Ng here, delta Ng is the number of gaseous moles, or we can say number of moles of gaseous products minus number of moles of gaseous reactants. Okay, so whenever a chemical reaction is taking place and gases are involved in that reaction, so basically delta Ng will give us the value of the difference of number of gaseous moles of products and number of moles of gaseous reactants, okay? We are never going to include any solid or liquid in this formula, right? Only gases. So delta Ng, R will be gas constant, T will be the temperature, constant temperature we know. Most of the time, generally, the chemical reactions are taking place at a constant temperature. So T will be the value of temperature, right? So these are the relations that we can use according to the question, according to the condition given in the question. It is chemical reaction, phase transfer, phase transition, or any other process, right? So first of all, we have to see the three conditions of delta Ng. So the conditions are, when the value of delta Ng is 0, means the number of moles of gaseous reactants and number of moles of gaseous products are same, then delta Ng will be 0. So in that case, delta H and delta E, these two values will become equal. They will become equal. Here delta E is basically delta U, okay? We can represent the internal energy in terms of E as well as U. So this is delta U, right? So these two will become equal when delta Ng is 0. For example, this reaction H2 gas plus I2 gas gives 2HI, right? So here number of gaseous products are 2 and gaseous reactants are also 2 moles, so 2 minus 2, 0, right? Second condition is when delta Ng is greater than 0, okay? So in that case, delta H will become greater than delta E or delta U. For example, this reaction here, the moles of gaseous products are 2, whereas for reactants we have 1 mole, so 2 minus 1, 1, so that is greater than 0. So delta H will become greater than delta E or delta U. And the third is when delta Ng is 0. So in this case, delta H will become less as compared to delta E. For example, here, this is the process where ammonia is getting formed. So nitrogen and hydrogen, these are the 4 moles. At the reactant side, at product side, we have 2 moles. So 2 minus 4, that is minus 2. Okay. So on the basis of value of delta Ng, we can find the relation between delta H and delta U. Enthalpy change and internal energy change. Fine. So now we have this question. So this is the best way to understand a concept and the application of that concept. Okay. So this question is basically a PYQ JEE 2022 question, right? So let's see and let's understand what this question is saying. So this question is, we have 2 moles of mercury gas, okay, is combusted in a fixed volume bomb calorimeter. Okay, so in this question we have this bomb calorimeter, right, having a fixed volume with excess of O2 at 298 Kelvin and 1 atmosphere pressure into HGO solid. Okay, so here we are combusting the mercury gas in excess of oxygen in a fixed volume bomb calorimeter, and this is the product mercuric oxide solid, right? During the reaction, temperature increases from 298 Kelvin to 312.8 Kelvin, right? If heat capacity of bomb calorimeter and enthalpy of formation of Hg gas are 20 kilojoule per Kelvin and 61.32 kilojoule per mole respectively at 298 Kelvin, the calculated molar standard molar enthalpy of formation of HGO solid at 298 Kelvin is x kilojoule per mole. So we have to find out the value of mode x, means we have to find out the value of this magnitude of x. Okay, fine. And here gas constant R value is given as 8.3 joule per mole per Kelvin, right? So how we are going to solve this question? First of all, we have to write the equation for the combustion of Hg gas. So mercury gas, when it is combusted, it will be reacting with oxygen and will be forming HGO solid. This is the reaction. If we balance this, we have to take 1/2 O2 gas, right? This is the balanced chemical reaction for the 1 mole formation of HGO, right? And here, what values are given? First of all, the 2 moles of mercury are given. 2 mole mercury. We have 2 mole mercury that is getting combusted in this reaction, right? And excess of O2 and temperature. If we talk about temperature, first the temperature was 298 Kelvin and it changes from 298 Kelvin to 312.8 Kelvin. So if we want to find out the value of delta T, change in temperature, so it will be 312.8 minus 298 Kelvin, that is 14.8 Kelvin. This is the value of delta T for this reaction, right? And what other information are given? Okay, delta H formation of Hg gas, this value is given to us, and that is, okay, 61.32 kilojoule per mole, and one more value is given, that is heat capacity of bomb calorimeter. So if we represent the heat capacity as C, so C value is given as 20.00 kilojoule per Kelvin. Okay, these values are given in the question, right? And we have to find out the delta H formation of mercury oxide. So what we can do? This is the complete reaction, and if I want to write the expression of delta H reaction for this whole reaction, what I can write? Delta H reaction is equal to, in terms of enthalpy of formation, what we can write? Enthalpy of formation of the products, okay, of products. So we have only one product, that is HGO. So delta H formation of HGO solid, okay, this is the product, minus delta H formation of reactants, right? So minus delta H formation of Hg gas, okay, plus delta H formation of O2 gas, multiplied with the stoichiometry, with the stoichiometric coefficient. This is the equation for the delta H reaction, right? And here one thing, this delta H formation of O2, this value will become 0. This value will become 0. Why? Because we know O2, oxygen gas, is already present in its standard state. So delta H formation for the substance which is present in its standard state is always 0, right? So this value is 0. So now what is left? Delta H reaction equal to delta H formation of HGO minus delta H formation of Hg gas, right? Okay. So now basically this value is already given in the question. This is 61.32 kilojoule per mole. This value is given. This is what we have to calculate. This is unknown for us, but delta H reaction is also unknown for us, okay? So we have two unknown quantities. One is given. So first of all, what we are going to do, we will calculate the value of delta H reaction, okay? Then we'll calculate the delta H formation of HGO solid, right? So now let's start. How to find out the delta H reaction? So we have bomb calorimeter. So in bomb calorimeter, the combustion is taking place at a constant volume. So we can find out the heat exchange taking place in the bomb calorimeter, and we know at constant volume, whatever heat exchange is taking place, that gives us the value of delta U, that is change in internal energy. So that's what we can calculate, okay? So let's see. In bomb calorimeter, at constant volume, we know that whatever heat exchange is taking place, that is equal to QV, and this QV will give us the value of delta U, and that is equal to heat capacity of the bomb calorimeter into change in temperature. Heat capacity of bomb calorimeter into change in temperature. But one more thing, we know that whenever combustion reaction is taking place, some amount of heat is always released. Combustion reactions are always exothermic in nature. So this amount of heat will be released. So that's why this will be having a negative sign, okay? This will be having a negative sign, right? So heat capacity is given 20 kilojoule per Kelvin, negative 20 kilojoule per Kelvin into delta T value. We have already calculated 14.8. So Kelvin will cancel out and we'll get minus 296 kilojoule. Minus 296 kilojoule. This is the value of delta U, right? But one very important thing is that this energy, this internal energy change is for 2 moles of HGO, okay? For 2 moles of mercury, this value is for, this is for 2 moles, but we have to find out for 1 mole, okay? We have to find out this delta U for 1 mole, right? Because we have to calculate the delta H also for 1 mole. So let's see, for 1 mole we can write delta U equal to minus 296 divided by 2, that is minus 148 kilojoule per mole, right? So we have got this value for the per mole. Now we have to use the relation to find out the delta H, that is delta H reaction. This is delta U reaction. So delta H reaction equal to delta U reaction. This is delta U reaction for the combustion reaction, right? Plus delta NGRT. Plus delta NGRT. Okay. So delta U reaction is minus 148 kilojoule per mole, okay, plus delta Ng value, okay, let's go back to the equation. What is the value of delta Ng? For this reaction, the value of delta Ng will be, this is solid, so this will be 0 minus, we have half and 1, so 3 by 2 moles of gas. So 0 minus 3 by 2, so we can say minus 3 by 2. This is the value of delta Ng, so we have to put this value in this equation. So this is minus 3 by 2, minus 3 by 2, okay, and into R. What value of R we have to place, because here it is in kilojoule, so we have to place the value of R also in joule, and that is given in the question 8.3 approximately, so we have to use this value 8.3. Now temperature, we have to calculate at 298 Kelvin temperature, so 298 Kelvin, right? But this whole value, this 8.3 is in joule per mole per Kelvin, so we have to convert this value also in kilojoule, so we'll divide this value by 1000, okay, and after solving this equation, you will get delta H reaction as minus 151.71 kilojoule per mole, okay. This is what you will get for the delta H reaction. Now we know only one step is left. Delta H reaction we have got, so we have to calculate delta H formation of HGO. So let's put that value in this equation. Delta H reaction equal to delta H formation of HGO solid minus delta H formation of mercury gas. Okay, this is what we have here in this equation. So delta H reaction is minus 151.71 equal to, this is what we have to calculate, delta H formation of HGO solid, and this value is given in the question, that is 61.32 kilojoule per mole, okay. So delta H formation of HGO solid is equal to minus 151.71, and this will become positive, so plus 61.32. So after solving this, you will get minus 90.39 kilojoule per mole, okay. This is the value of delta H formation of HGO solid. Now we have, this is the value of X, according to the question. So we have to find out magnitude of X only. So this will be 90.39, okay, and this will be the answer of this question, okay. So this is how we can apply this relation to solve such kind of questions, okay. Now let's move forward. Let's talk about the next topic, that is entropy, okay. So before going forward and solving the questions related to entropy, we have to understand few things like what is entropy, and we have to see the basic formulas of the entropy, right? So let's see. Entropy, we know it is a state function given by the second law of thermodynamics. So entropy is given by second law of thermodynamics, and it is a state function. It does not depend on the path of the process, whatever process is taking place, it does not depend on the path, depends only on the initial and final states, right? Second, entropy gives the measure of randomness. Now what is the physical significance of entropy? It gives the measurement of randomness of any system, okay, or disorderness also, measurement of randomness or disorderness of a system. Now second law in terms of entropy, if we just look at the statement of second law in terms of entropy, then it says that in a spontaneous process, entropy of universe increases, okay. So if we have a spontaneous process, then entropy will be increasing, the entropy of universe will always be increasing, right? So when you have spontaneous process, delta S universe equal to delta S system plus delta S surrounding, this should always be greater than 0, right? Because delta S universe always increases for the spontaneous process according to the second law. Now, for a non-spontaneous process, the sum of these two values will become less than 0, Delta S universe will become less than 0 means it decreases for a non-spontaneous process. Or we can say the opposite also, when delta S universe is less or negative, it is decreasing, that means it is a non-spontaneous process, right? And when you have a reversible process or a process at equilibrium, then delta S universe will be equal to 0. So sum of these two values, delta S system plus delta surrounding, this will become equal to 0, okay? Or we can say delta S system is equal to negative of delta S surrounding, right? Now let's see entropy change of an ideal gas. If you want to talk about the entropy change for an ideal gas for different processes, then these are the basic formulas that we can use. First of all, delta S equal to NCV ln T2 by T1 plus NR ln V2 by V1. In terms of volume, if you want to place pressure, then in place of CV you have to write CP. So NCP ln T2 by T1 plus NR ln P1 by P2. Okay, here you have V2 by V1, but here you have to use P1 by P2. Second, delta S surrounding. This is for the system. This is for delta S system. Delta S surrounding will be initial to final state dq surrounding divided by T surrounding. Now dq surrounding, whatever heat exchange is taking place between the system and surrounding, that will be same. So dq surrounding is equal to the negative of dq system. Okay, suppose system is losing 10 kilojoule energy. So for system it is negative, but surrounding is accepting it. So for surrounding it will be a positive value, right? So negative of dq system divided by, now temperature of surrounding is the final temperature of the system. So T2 can also be taken as T surrounding, right? So this formula we have to use to find out the delta S surrounding, okay, for the irreversible process, okay? And because for a reversible process we know, or equilibrium, delta surrounding and delta system both are having same magnitude, just with a negative sign, just with opposite sign, the magnitudes will be equal. So basically this formula you have to use for irreversible process. For irreversible process. So for irreversible process you have to find out the delta system and delta surrounding separately, okay? Now when you have isothermal process, now if we apply certain conditions like temperature is constant, pressure is constant, volume is constant, then how we can use these formulas? So basically when you have isothermal process means temperature is constant. For an ideal gas, temperature is constant means delta T will become 0. So basically the temperature term, if you will see this formula, this temperature term, this term will become 0. So only this term will be left, okay? And here also this term will become 0. So basically the formula becomes delta is equal to NR ln V2 by V1 or NR ln P1 by P2. And when you have reversible process, so delta surrounding will be negative of delta S system, right? And when you have irreversible process, so for the system the formulas are same. When you are calculating the delta S system, either for reversible or irreversible process, the formula will be same, okay? The value of the delta system will be same. But for the surrounding, here you just have to reverse the sign, but here you have to calculate separately using the formula delta S surrounding equal to negative of dq system by T surrounding, right? Now delta S for isobaric process. When you have isobaric process means pressure is constant. Here pressure is constant. Pressure constant, this is for ideal gas again. So reversible process, so you have to use the formula delta is equal to NCP ln T2 by T1, because that P1 by P2 term, that will become 0. So NCP ln T2 by T1 and delta surrounding will be negative of delta S system. And for irreversible isobaric process, delta is equal to NCP ln T2 by T1, okay? For system it is again same, but for surrounding we have to use again the same formula, right? Now if we talk about isochoric process, isochoric means volume is constant. Now volume is constant. So for reversible isochoric process, delta is equal to NCV ln T2 by T1, because that V2 by V1, that part will become 0. So delta is equal to NCV ln T2 by T1 or delta surrounding is negative of delta S system, the same thing. Similarly for irreversible, delta S system is as it is, but delta surrounding, again the same formula from initial to final state minus dq system divided by T surrounding. Okay, so whenever you have irreversible process, you have to be careful while calculating the delta S system and delta S surrounding, right? Now, if we talk about the adiabatic process, so for the ideal gas, so we know that in adiabatic process, the Q, heat exchange is 0, Q is 0. Whatever heat exchange we are talking about, that heat exchange value will be 0, because in adiabatic process, no heat exchange is possible, right? So, if we talk about reversible adiabatic process, then delta S equal to 0, because the process is adiabatic reversible. So, Q reversible value, this value will become 0. That's why delta S becomes 0. Delta S system becomes 0. And delta S surrounding will also become 0, because Q reversible, the heat exchange for system as well as surrounding, this is 0 in reversible process. So, that's why both are 0, and delta S total will also be 0. Okay. But when we talk about irreversible process, then delta S system is not equal to 0. For irreversible process, we have to calculate the value of delta S using this formula, NCVln T2 by T1 and NRln V2 by V1, right? Or P1 by P2. And delta S surrounding, we have to find out by using the same formula, dq system minus dq system by T surrounding. Okay. And yes, because for reversible adiabatic process, when we talk about the delta S surrounding, here also the dq system is 0. Okay, dq system, because whenever you have the adiabatic process, so dq system will also always be 0. So because in delta surrounding formula you have this dq system term, so that's why this will become 0. So for irreversible adiabatic process, delta S system is not equal to 0, but delta S surrounding is equal to 0. So sum of these two means, if I am talking about delta S universe, so delta S universe will be equal to delta S system only. Okay, because for surroundings the process is always reversible. Okay, so that's why when we talking about the adiabatic process, the delta S surrounding is always 0, because for surrounding all the processes are of reversible nature, because surrounding is huge. For system, the process can be reversible or irreversible, but for surrounding, it is always reversible, right? So these are the all formulas. Okay. Now this is very important point. You have to keep this point in your mind. Okay, that never use these relations, PV gamma equal to constant, TV gamma minus 1 equal to constant, and P1 minus gamma T gamma equal to constant. Never use these relations for irreversible adiabatic process. These relations are only for, these are used only for reversible adiabatic process. Reversible adiabatic process. Okay, so never use these relations in irreversible adiabatic process. Okay, fine. Now we have seen all the formulas, so now let's try to solve the question based on entropy. Okay, so let's see this question. 2 moles of triatomic non-linear ideal gas. Okay, we have a triatomic non-linear ideal gas, and we have 2 moles of this gas, and CV for this is 3R, CP is 4R, and gamma is 4 by 3. It is given, was expanded adiabatically from 16 atmosphere 300 Kelvin to 1 atmosphere. Calculate the value of delta S surrounding, and delta S universe. Okay, if the process is reversible, irreversible, or free expansion. So 3 different conditions are given, and we have to find out the value of delta S for each case. Okay, and delta S system, delta S surrounding, and delta S universe. So let's start solving this question. First of all, if we talk about the reversible process, so reversible adiabatic process. Reversible adiabatic process. So we have just seen this, that whenever you have reversible adiabatic process and you are calculating the entropy change, then it will be 0. Delta S system is 0. Delta S surrounding is also 0. And delta S universe is also 0. This is also 0. When you have reversible adiabatic process, because the heat exchange is 0 in this process, right? So all these values will become 0. So first we have already solved. Now let's see the second part of this question. When you have irreversible process, irreversible adiabatic process. In irreversible adiabatic process, we know delta S system is not equal to 0. Delta S surrounding is 0. Because for surrounding the process is always reversible, so delta S surrounding is 0. So how we can find out the delta S system? Delta S system, we have to use the formula that is NCP ln T2 by T1 plus NR ln P1 by P2, because here change in pressure is given 16 atmosphere to 1 atmosphere. That's why we are using this formula. Okay. So here temperature T1 is given 300 Kelvin, but temperature T2 is not given in the question. So first of all, we have to find out the value of T2 temperature. Then we will put that value in this formula to find out the final answer, right? So to find T2, what we have to do? To find T2 temperature, what we can do? We have seen that we cannot use those relations PV gamma equal to constant and TV gamma minus 1 equal to constant. We cannot use those relations for the irreversible process. So what we can do here? We know for adiabatic process, we know delta U is equal to W from using the first law of thermodynamics, because Q equal to 0. Because Q is equal to 0, so using the first law of thermodynamics, we know delta U equal to W, right? So we have to put that these values here. Delta U is equal to NCV dt, and work done is negative P external dV. Okay, so if we place the value NCV for this gas is given in the question, that is 3R. So N into 3R, and dt is T2 minus T1, okay, equal to minus P external dV. So P external is not given. So when P external is not given, the final pressure P2 can be considered. Final pressure P2 can be considered as P external, right? So in place of P external, we can write P2. Okay. Now this dV will be V2 minus V1. But volume change is not given. Initial or final volume is not given in the question. Then what we can do? This ideal gas is given. So we can use the ideal gas equation, PV equal to nRT. So from here we can replace the volume by nRT by P. So in place of V2 minus V1, what I can write? I can write nRT2 divided by P2 minus nRT1 divided by P1. This is what we can use here to solve this equation, and now we have to calculate the value of T2, right? So first of all, we can say that nR will be constant, so nR into 3 T2, and T1 is 300 Kelvin equal to minus, we can take the nR as constant, so minus nR P2 T2 by P2 minus T1 by P1. Okay, so this nR will get cancelled out from both sides, right? So now what is left? So let's write it here. Okay, so basically we have here 3 T2 minus 300, so this can be written as 3 T2 minus 900 equal to we have P2, and if we multiply the P2, so it will become T2 and with negative minus T2, because you have negative sign also. So minus T2 plus P2 T1 divided by P1. Okay, this relation we have got. Fine. So now let's solve it. T2, if we take at this side, it will become 4T2 equal to, and if we place the value of P2, final pressure is 1 atmosphere. So 1 into 300 is the value of T1 divided by P1 is 16. When you take 900 at this side, it will become positive, so plus 900, okay. So now basically you have to solve this equation to find out the value of T2. And after solving this, the value of T2 that you are going to get will be 229.68 Kelvin. This is what you are going to get after solving this equation. This is the final temperature, and this is low temperature, you know, because expansion is taking place. So we know in adiabatic expansion the temperature of the gas decreases. So this is the value of T2. Now we have to just place this value in the formula of delta S system to find out the final answer. So delta S system is equal to, okay, you have NCPLN. So N is number of moles are given as 2. Cp is 4R, okay. So 4R. Ln T2 is 229.68 divided by, okay, T1 is 300 plus NR ln P1 by P2. So N number of moles 2 into R into P1. P1 was 16 atmosphere. So ln 16 by 1, okay. Now you just have to solve this equation to get your final answer, delta S system, right? And we have already calculated delta S surrounding for the irreversible adiabatic process is already 0. So delta S universe will be equal to delta S system only, because delta S surrounding is 0. So we have solved the second case. Now the third case, that is free expansion. So in free expansion, what will be taking place? What will be happening? So third process is free expansion. So we know in free expansion, when free expansion of ideal gas is taking place, we know the P external is 0. P external is 0. Work done is 0. Heat exchange Q is 0. Okay. And delta T, there is no change in temperature. So delta T is also 0. All these values are 0 for the ideal gas when we are talking about the free expansion, right? So here, that's why we call it as adiabatic as well as isothermal at the same time, because there is no heat exchange. So adiabatic, no temperature change, that means isothermal. So that's why free expansion of ideal gas is adiabatic and isothermal at the same time. So here, if we talk about the delta S surrounding will be 0. Because the Q, heat exchange for the surrounding is 0, right? Q is 0, that's why delta surrounding is 0. But delta S system is not equal to 0. Why? Because heat exchange is not taking place, but volume is changing. In free expansion, volume is changing, and due to that volume change, entropy will be changing, entropy will be increasing, right? So that's why entropy change will be there for the system, and you can find out this value by using the formula NR ln V2 by V1 or NR ln P1 by P2, okay? Because temperature is constant, so V2 by V1 can be written as P1 by P2 also, right? So we can use this formula to find out delta S system. Moles are 2, R into ln P1 by P2. So initial pressure was 16, final is 1, okay? So now you just have to solve this equation to get your final answer, okay? This is how we can use the formulas of entropy change to solve the numericals, right? Now, let's move forward. Let's talk about the next topic, that is variation of enthalpy with temperature, that is called as Kirchhoff's equation. Kirchhoff's equation, okay? So enthalpy also depends on the temperature and how it changes with respect to temperature. So let's see. When we talk about chemical reactions and phase transition, the enthalpy varies with the temperature. Enthalpy varies with the temperature. Although the variation in delta H with temperature is usually small as compared to the value of delta H itself. So the change is not much. The change that is taking place is a small value, but still some change will be taking place, and we can find that out by using this equation, Kirchhoff's equation. So basically, what is this Kirchhoff's equation? It is delta H2 minus delta H1. Delta H2 minus delta H1 equal to T1 to T2 when you are changing the temperature, delta Cp delta Cp of the reaction, delta Cp reaction dt. Okay, this formula can be used to find out the change in final enthalpy change, that is this delta H2 is at T2 temperature, and this will be at T1 temperature. Okay, so this equation is called as Kirchhoff's equation, and this is at constant pressure. This is at constant pressure, when pressure is constant. Okay, but when you are calculating this or applying this formula at constant volume, then in terms of internal energy change also the same formula can be written, delta U2 minus delta U1 equal to T1 to T2. In place of Cp, we can write Cv at constant volume. So delta Cv of reaction into dt. Now what is this delta Cp or delta Cv? Okay, this is first of all at constant volume. At constant volume. Now what is delta Cp or delta Cv? Delta Cp of reaction. Delta Cp of reaction. This can be calculated as sum of Cp of products, summation of all the values of Cp of products minus summation of all the values of Cp of reactants. Cp of reactants. Okay, by using this formula we can find out the value of delta Cp reaction, right? This is the Kirchhoff's equation. Now let's see how we can use this equation and how we can solve the questions related to Kirchhoff equation. So we have this question. The question is, enthalpy of sublimation of iodine is 24 calorie per gram at 200 degrees Celsius. Okay, if specific heat of iodine solid and iodine vapor are 0.055 and 0.031 calorie per gram per Kelvin respectively, then enthalpy of sublimation of iodine at 250 degrees Celsius in calorie per gram will be. Okay, so very simple, we have to directly apply the formula, the Kirchhoff's equation. We are talking about the delta sublimation. So basically here we are converting the iodine solid to iodine gas. This is what sublimation is. So delta H sublimation at 200 degrees Celsius is given in the question, that is 24 calorie per gram. Okay, fine. And here the value of Cp, specific heat is given. Specific heat is given for the iodine solid. Okay, specific heat S is given for the iodine solid. It is 0.055. Okay, 0.055, and for iodine vapor or gas it is 0.031 calorie per gram per Kelvin. Fine. So we can directly apply the formula here. We have to find out the delta H at 250 degrees Celsius, that is delta H2. Okay, so minus delta H at 200 degrees Celsius. This will be equal to delta Cp reaction. So delta S, here specific heat is given, so we can write delta S reaction, or specific heat. Specific heat can also be written as Cs, so you don't get confused with the entropy. So I'm writing Cs here. So delta Cs for the reaction. Okay, and this will be T2 minus T1. Okay, dt, T2 minus T1, right? So let's find out delta H at 250 degrees Celsius will be equal to delta H at 200 degrees Celsius, that is 24 calorie per gram. Okay, plus delta Cs reaction, what will be the value of this? Product minus reactant, value heat capacity of product minus reactant. So product is 0.031 minus 0.055. Okay, and T2 minus T1. So the change in temperature, 250 minus 200. Okay, so change in temperature is 50, right? Now you have to solve this, and you can see that here you are going to get the negative value Okay, you are going to get the negative value. So 24 minus something. So this value will be 22.8. The final answer will be 22.8, and this answer will be in calorie per gram, and this is given in the fourth option. So that's why here fourth option will be the right answer. Fine. So this is how we can apply the Kirchhoff's equation to solve these questions. Right. So now that's it from my side on this topic. If you have any query or suggestion, you can write in the comment box, and don't forget to watch the complete series. The link of the playlist is given in the description, right? So feel free to reach out to us. We will surely revert you back. So fine, I'll see you in the next video. Take care. Thank you.